Hey everyone, and thanks for joining today's session on automating production level machine learning on AWS. My name is Mark McQuaid. I'm a practice manager with Onica within our data science and engineering practice. Within our practice, we focus on all things data, all things machine learning. And today I wanted to take you through our solution to the emerging challenge of operating machine learning models in multiple environments, taking them from development all the way to production. So we named the solution the Machine Learning Model Factory. So just a quick intro to Onica. So an all-in APN premier consulting partner. So all-in meaning AWS exclusive, 100% focused on helping customers be successful within the AWS cloud. We feel we've developed a certain mastery of the platform and strategically chose to do this with AWS based on the breadth of services. Cloud native thinking, everything we do is cloud native first and foremost, delivering results that leverage the full power of the cloud. Outcomes designed to last, right? So we ensure the cloud keeps delivering value without rework long after we've wrapped up an engagement. And we're all about the people, right? We approach all our projects very collaboratively. This allows us, for the teams we work with to gain new skills and continue down the path to success we have started together. And as you can see on the right, we have achieved a number of AWS competencies, which allow us to drive our customer success wherever they are in their cloud journey. And also something worth pointing out is the 1,600 plus AWS certifications that we have in-house. That's something else we're really proud of in-house. All right, so a little bit about operationalizing machine learning models, right? So this can be challenging, right? It's not a very simple thing. People often underestimate the effort involved in bringing machine learning models from development, in that development stage, all the way to production. So here's just some of the challenges: deployment, automation, and scalability, right? Getting machine learning models from a dev environment to a production environment quickly is typically not something data scientists focus on, right? This is more of a DevOps or infrastructure team thing. Reproducibility of models and predictions. So it can be difficult to reproduce a model's output when moving it from one environment to another. This requires careful tracking of library versions and data sets. Diagnostics, performance monitoring, and model drift. So it's most likely your data scientists will have multiple models running simultaneously in multiple environments using different data sets and different hyperparameters. So this makes it virtually impossible to track a model's lineage. Explainability for governance and regulatory compliance. So one of the most important aspects to governance and regulations, especially when dealing with auditors, is tracking and explaining everything your model has done or is doing. Collaboration. Right? So data science teams often face challenges in how they manage models as they pass through the different stages of the machine learning workflow and pipeline. So this could be with respect to model versions, annotations, or even model history. So as you can see, there's many challenges that a business may face when trying to operationalize their machine learning. It's, as I mentioned, it's not simple, it's not clear cut. And it's worth mentioning, a telling stat there at the bottom of the screen: 60% of machine learning models never actually make it to production, right? So you spend all this time developing a machine learning model that fits your business needs, but never actually gets to production to get that ROI. So the agenda for today, we'll talk a little bit about why customers need ML operations in general. Then introduction to the model factory framework itself. We'll talk just through some features of it, how it works. Then we'll go through a customer success story, customer benefit, and then Q&A to wrap it up. So we've entered an age where no business plan is complete without an ML strategy, right? Companies are realizing the value of using machine learning to better drive outcomes for their business. So in addition to using their data in a reactive mode with business analytics tools, companies are now harnessing the predictive power of their data with machine learning. As a result, ML models are becoming as an important tool in business operations as data processing and data analytics tools were and have been really for the past decade. As well, getting your ML models to production in a timely manner is key. However, developing domain-specific ML models is only the first step in your strategy. Operationalizing your models, as I touched upon before, and taking those models to production to drive business insights is more complex than many people think. So what we see today in a lot of organizations is that there's a lot of research and development gets sunk into that model development stage. However, the models never do make it to a production environment, right? This could be from many factors, but what we see most is the disconnect between the operations or data ops teams and the ML engineers. That's kind of that gap. Another common problem is models tend to increase. So models tend to multiply based on use case and into different environments as well. So think of a bank operations as one example, and the number of different areas that can benefit from predictive analysis, from identifying fraudulent transactions all the way to risk assessments on mortgages, okay? So data scientists will create domain-specific models and run many experiments, first in a dev environment and then move them to a testing environment. So this results in multiple models running simultaneously across different environments using different data sets and different hyperparameters. And again, I'll say it again, this is where it comes in, it becomes virtually impossible to keep track of a model's lineage without an operational solution in place. So we hear a lot from our clients that it might take them just a few weeks to develop that good machine learning model that addresses their business needs. Yet it takes them months to get that model deployed to production. So our clients were looking for a solution that would combine data prep, model training, deployment, model monitoring, all in one workflow or framework across multiple environments, all while maintaining strong governance and security controls. So you may say that's DevOps, right? Essentially DevOps. Well, why is DevOps not enough? Right? So the DevOps culture and application lifecycle management have become a standard in the IT industry over the last decade. It emerged to fill the gap between the organization's ability to develop application code and the way to efficiently deploy, update, test, scale, and monitor those workloads. So mature CI/CD pipeline needs are largely addressed in application development by the industry-wide standardized tools and best practices there are out there now. But unlike application development, where the quality comes from the code itself, the quality of a machine learning model comes largely from the data features used to train it. So the importance of these data features cannot be understated. Their quality drives a machine learning model's performance. And it's worth mentioning, ML models are really still in their operational infancy. So additionally, something to keep in mind is data might change daily, and the data that was used for predictions today might be significantly different from the data used for training a model a month ago. So in that case, your production model would then need to be retrained and go back into that development phase. As a result, a machine learning model's lifecycle is significantly different from that of an application lifecycle. In fact, we actually had a customer in fraud who wanted to push production models every 24 hours to account for new threats. So the customer would retrain and redeploy their model every day to account for this drifted data. And that, again, is impossible without a mature solution for model operation. So there's many steps to an entire machine learning lifecycle, as you can see here. Each step has its own set of challenges. So you have data ingestion, data analysis, data transformation, then you're gonna validate your data, you're gonna split your data, then you're gonna start your training process, you're gonna build a model, you're gonna validate that model, then you're gonna train it at scale, of course, then you'll roll it out, you'll serve the model, and then you're gonna obviously monitor its performance and then logging all results. So, the machine learning lifecycle is complex, right? And with all these steps and their associated challenges in mind, that's the reason behind why we developed the Model Factory framework. So with that, I'd just like to introduce the Amazon ML stack. So AWS sinks a lot of energy, resources, and time into their AI platform, and it's really turned into their flagship offering, right? Their go-to product. So as you can see on this slide, it's a 3-layer stack. So you have your AI services layer, your ML services layer, and your ML frameworks and infrastructure layer. So your top level layer, your AI services layer, is your pre-built out-of-the-box solutions that are ready to go, right? You don't have to be a data scientist or an ML engineer to use these services. And AWS's slogan is they want to put AI in the hands of all developers, right? So these are ready to go. And they cover different domains, right? So from vision, you have Amazon Recognition, to speech, which Amazon Poly and Amazon Transcribe. Language services such as Translate, which is a translate service, of course, Amazon Comprehend, which is an NLP service, chatbot service, which is Amazon Lex, and some of the newer services, Amazon Forecast for time series forecasting, and recommendation is Amazon Personalized, which is a recommendation engine. This is not the full list by any means. There's a lot more services than that, but just to get a feel for what those pre-built services are. The second level layer is the ML services layer. So this is your Amazon SageMaker layer. And for anyone who doesn't know what SageMaker is, it's AWS's end-to-end machine learning platform, right? So it gives you the ability to build, train, and deploy your machine learning models all within that one-stop shop within the SageMaker ecosystem. And then the third layer is the ML frameworks and infrastructure layer. So that is for full control by your data scientists or your machine learning engineers. So they don't have to work within the confined space of SageMaker. So let's think of an EC2 instance, probably a GPU-backed EC2 instance running a deep learning AMI, and then you have full control, right? You log into it, you run your own framework of choice, and that could be TensorFlow or MXNet or PyTorch. And that could be, you could use some interfaces such as Glue or Keras, and it's completely up to you. And you don't have to, as I said, work within that confined space of SageMaker. So a lot of data scientists and ML engineers prefer working at this layer, the ML frameworks and infrastructure layer. So, as you can see, AWS tries to check all boxes when it comes to using their platform for any of your ML needs. But it's worth noting that the Model Factory framework can also function outside of these layers, outside of this ecosystem. For example, services like EKS can be used for the Model Factory framework, which is Elastic Kubernetes Services, which is managed K8s, or Amazon EMR, which is Elastic MapReduce, which is managed Hadoop. So it's not confined to this layer, all these layers or this ecosystem. And one aspect that's not quite mature in this stack is the lifecycle management and integration components that allow for orchestration of machine learning, right? Additionally, we truly believe that each customer is different and should have the flexibility to choose their own platform based on their existing processes, their existing tooling, and of course, their existing skill set. So while AWS does provide a great set of services for machine learning, some clients may still require end-to-end machine learning blueprints and the ability to run across different platforms for these. So with that, introducing the Model Factory framework, cloud-based machine learning lifecycle management solution. So what is the Model Factory framework? By definition, the Model Factory is a machine learning operations framework built on AWS using open source tools that enable rapid development, training, scoring, and deployment of models. So if you can see all these squares and rectangles in this side and everything that's in them, this is everything that's wrapped up into the Model Factory framework, right? The Model Factory itself is more of an architectural pattern than a product. It was built to address the problems our customers were facing when taking machine learning models from development to production. Now, one of the driving forces from within Onica behind this was a peer of mine named Gus Mohammed. He goes by Mohammed. He was kind of the driving force and the brains behind the Model Factory. So I like to throw in a quote from him when I do talks on this. And Mohammed says, the primary motivators for the Model Factory were to bridge the gap between data science and operations, and also to reduce the time to get ML models deployed into production, right? So the premise behind it's extremely simple, but it's extremely complex to get them, the models from point A to point B. So the solution again is built with open source tools and is a flexible framework that allows integration with AWS services as well as industry standard automation tools for data processing such as Airflow, Jenkins, AWS Code Pipeline. It's also worth mentioning that the main concerns of a model's governance across multiple environments have been addressed through the experiments tracking, which is visible through a tracking UI. Model Factory supports deployment of models into different hosting platforms, such as K8s, as I mentioned, or SageMaker. It supports a variety of frameworks that could be TensorFlow, that could be Scikit-learn, Spark ML, Spacy, PyTorch. The solution is highly extendable and can be customized based on the business needs and domain requirements. So I'm just going to go through, some of the challenges I listed earlier on the slide and how Model Factory solves those challenges, some of the benefits, right? So standardized model development environment for your data scientists. So no more multi-environment model deployments and no need for data scientists to worry about which environment to put their model. Automated deployment across dev, QA, and prod. Everything starts out in a dev environment, and through automation, everything gets promoted, when ready, of course, to the next stage and environment. Reproducibility of models and predictions. So this allows for data scientists to easily duplicate models and model outcomes in many environments. Tools for diagnostics, performance monitoring, and addressing model drift, which is big. Model Factory allows for complete tracking of your model, allowing easy access to diagnostics, performance of that model, and catching any of that model drift. Model lineage for governance and regulatory compliance. So Model Factory also captures all model lineage for easy details, description, or explanation of your model, and that could be with auditors, as I mentioned earlier. Platform for collaboration across data science teams. So data scientists no longer have to work in individual silos, which happens quite often right now. Accelerated ROI and faster time to business insights. So Model Factory allows you to take those models into production in a timely fashion, right? And that's what you want. Allows you to get that return on investment you envisioned when you decided to start using machine learning in your business in the first place, really. So the model development lifecycle here, I just wanted to talk a little bit about what that looks like without Model Factory and then with Model Factory. So without Model Factory, the whole lifecycle could take months, right? It could be 25 plus steps. Everything's going to start in a local dev, and then it's going to get promoted maybe to a cloud dev environment, then QA, prod, right? So with Model Factory, that's reduced to just weeks with 10 or so steps. Manual handoffs between various teams without Model Factory. So with Model Factory, automated deployment between environments with controlled access to data teams needed for specific steps, right? So everything's automated and everything has tight access. Cycles of troubleshooting between data scientists' local dev environment and data engineers' environment. So with Model Factory, that's not the case. You have one source of truth for experiment tracking, project packaging for easy source control and reproducibility. So here's the four kind of pillars of Model Factory. It's kind of broken out into 4 sections, and it's all under the Model Factory umbrella. You have your model development, your model deployment, then monitoring and governance, right? So as time is short, there's going to be some certain topics that I may just skim over. I won't get into too deep of details on these, but I will go into each one. So from a model development standpoint, right, you have the ability to develop in an agnostic of the development environment, right? Ability to easily onboard existing models into the Model Factory using curated list of notebook templates and proprietary manifest DSLs. They cater to different use cases. And I'll show an example of a DSL that I just mentioned on the next slide. Ability to recreate both training and scoring environments with ease. Ability to track and tune both manual and automated hyperparameter tuning jobs. The ability to consistently package models and model code agnostic of the domain. The ability to test multiple versions of the same model in a QA environment for performance and degradation. And the ability to debug, right, and exit long-running model training jobs early, which are not performing for a given set of features. So here's just a look at the model DSL that I mentioned on the previous slide. So as you can see, it gives you a full list of details about the model name, the type of container definitions, entry point information, to the actual resources used for different environments. It also includes mechanisms to request spot instances if you're wanting to use spot instances for your deployment, or ephemeral EMR as well, or Kubernetes pods, right? So essentially the brain of the Model Factory infrastructure is all in this model DSL, which is why I wanted to show it and highlight it. Now, in the model development stage, one of the big pieces is development environment, right? So when you talk about ML engineers or data scientists working, you would likely see they tend to be very attached and opinionated as well about the development environment that they get the most out of in terms of features or user experience, and they may have accumulated these experiences over years working with the same tool. So there are 3 primary model environments we cater to within the Model Factory. That's notebooks, IDEs, and finally an automated environment using AWS tooling, and that could be AWS native developer tools, it could be Jenkins, right? So our recommendation has always been to cater to the team's existing development environments and their existing skill sets, as opposed to making them learn something new. All right, so another piece to the model development is the integration, right? So 2 main added advantages here is based on our extensive experience working with different data ops teams, ops teams, or even soon to be ML ops teams. We've created notebook templates and scaffolding to allow for easier onboarding. So what exactly is that? So notebook templates allow data scientists to place their existing code into predefined placeholders and run the model against our centralized tracking server. So essentially, this allows data scientists to be abstracted away from the complexity of the underlying platform and the infrastructure as well, where the code runs. It allows them to focus on writing code to build models, which is what a data scientist does and wants to do. Additionally, we provide scaffolding, both scripts and the DSL that I showed earlier to allow easier build, train, and integration with notification systems for training, also for deployment, and as well that falls in with monitoring as well, monitoring the model onto a desired platform. Those DSLs that I showed really just allow us to bridge that gap, right? It's really the bridging that gap between the operations teams and the data scientists or machine learning engineers. So dependency management. So data scientists need to be able to run the same model training against different hyperparameters to evaluate how the model is performing, right? So one other challenge that machine learning engineers face is the expectation that they're able to reproduce the training runs if they so desire, or even share that environment with other data scientists who are able to then recreate the environment. So we recommend, and we use tools such as Conda and Docker images to help with this regard. So Conda has obviously been well tested, of course, and is a proven tool in the data science space. And one interesting use case that we came across actually was a customer who did not have internet access in their model development environment. So what we did is we used a pre-built Docker container, which essentially packaged all the dependencies. These Docker images are stored, we stored them in AWS Elastic Container Registry, which is think Docker Hub within AWS. And we used a private network for that. So we also designed container image rollout architecture as part of the CI/CD pipeline. So definitely an interesting use case. Tracking and tuning. So tracking to a centralized server becomes critical to data scientists. So traditionally when data scientists run experiments, the data or the parameters with which data scientists worked with can be lost with no traceable revision history. So even though we have a mechanism to reproduce the experiment environments using tools such as Conda, they do not know the flags provided to the program. They don't know the hyperparameters or the dataset version even. So to solve this issue, we have to allow proper tracking of model runs. So we have mechanisms to track not just the general runs, but also to log hyperparameter tuning runs and compare them using a plot. So besides that, there's also enhanced logging and metrics for popular frameworks such as TensorFlow or Keras and so on. So this allows for data scientists to dig down into the detailed metrics, such as looking at the loss or accuracy per epoch. And the callbacks that are set up will be able to automatically log a summary and import metrics for the model over the course of the training run. So consistent packaging. So we talked how we solve the replicating or reproducing model training environments issue. However, we haven't talked about replicating model inference environments or how we handle the idiosyncrasies of different ML frameworks. So for example, binary format for TensorFlow-based models would be different from that of PyTorch. So besides, it's not just the model itself. We have additional artifacts like plots, metadata about the model, or dependent scalars that could be Pickle or HDF5 format. So there needs to be a consistent mechanism to package the model or models and their associated artifacts and target different platforms, or else the operators would need to concern themselves with details on how to serve different types of models and formats. The Model Factory allows for and provides all this consistent packaging. A and B testing. So now that you have a model developed and trained, the next step is testing the model, of course. With proper testing on a different data set, we would not be certain we would have not overfit the model. So we need to confirm the accuracy and loss percentages. So with this step, we provide a different data set or even a better snapshot of the actual unlabeled production data. And after sending the data for prediction, we capture the requests and responses over a range of time and compare it to the data set's ground truth. So this way we're able to assess the true model performance. Now in some systems, we can take this even further actually by testing multiple model endpoints and comparing the model performance over a given period of time. Now, if you notice a pattern, you can imagine this process can also help us do real-time model monitoring and production model performance as well, right? Okay, so on to deployment. So that was kind of all wrapped into the development piece of the Model Factory, which is primarily the biggest piece. But there's also those 4 pillars, right? So the second pillar is model deployment. So as you can see on this screen, things that are involved in the deployment stage, you have supports multiple platform backends for same model code, right? So that could be deployment to SageMaker, as I discussed earlier, EMR, ECS, which is the Elastic Container Service from within AWS, EKS, which is the Kubernetes service, as I touched upon earlier. It supports promotion view, right? So from dev stage prod, everything gets promoted. Tracks revision history on all upstream artifacts and notebooks. And it supports real-time, batch, and streaming inference pipelines. Okay, so training or inference pipeline specifically. A common question we get from customers is, how does the ML pipeline tie into the existing data ingestion or data transformation pipelines? So a typical ML lifecycle contains steps around feature engineering, feature enrichment, things like that, minor pre-processing, or even post-processing. So when there are 2 or 3 data pre-processing or post-processing steps, they tend to use orchestration tools, right? And that could be Airflow as one example. Another use case is where customers have not one model, but they use multiple models and multiple estimators to get the generalization. However, it's not a single model, but a combination of these models in a sequence or based on some business criteria. So this can be very common in an organization, right? Recently, we've actually seen 3 to 4 organizations that do this extensively. So in such scenarios, you need a state machine of some kind to orchestrate a workflow. So we do provide support for popular frameworks such as the Data Science SDK, which is step functions within AWS, also Apache Airflow, right? A huge orchestration tool is Airflow, or Argo for that matter. So from a monitoring standpoint, we look at 3 main domains involved, right? So you have your infrastructure, your platform, and your data model monitoring. So you're able to capture model requests and responses for comparisons for detailed analysis. Data quality metrics are captured using Apache DQ. And then, as I mentioned, infrastructure monitoring as well, using things like CloudWatch, Datadog, and a few other partners are supported. Governance and security. Right? So this is the last pillar within the Model Factory framework. So clear separation of data and model artifacts, granular access controls using AWS IAM and bucket policies, rule-driven access based on Amazon Cognito, or it could be any other IDP. IAM authentication for back-end data stores, right? So that could be RDS. Cryptographic keys using KMS, the key management service. Data lineage and traceability using tools like DVC or Delta Lake. And extensive use of tagging for auditing and accounting, right? That's big. And that's all wrapped into the governance and security pillar. Okay, so a little bit, I just wanted to show a visual. Some people are visual thinkers. I'm one of them. So I like to, show a visual and kind of just really quickly summarize what it looks like. So this visual right here is a sample Model Factory architecture diagram, okay? This could be, like I said, Model Factory is very customizable, so this could be, exactly what someone may be looking for or drastically different from what someone's looking for, right? But the premise behind it's all the same. So in the development phase, data scientists perform exploratory analysis of the data and the model. They then evaluate the enriched features, choose an appropriate algorithm for the problem domain, and they may develop locally, as I said, in an IDE or remotely in a Jupyter Notebook solution of their choice, right? Completely up to them. At the staging QA stage, data scientists feel sufficiently confident about the model. They wish to test the model using a larger production data set. And this data set has undergone sufficient refinement to comply with the organization's security and compliance, let's say. In order to facilitate the testing, all the data scientist needs to do is wrap up a sample blueprint project file, right? One of the DSL files that I showed earlier, and the model code, of course, and then push it into the Git repo into the staging branch. At the production stage, data scientists have evaluated and tuned the final model algorithm against the production data set under various hyperparameters. The data scientists and the operations teams have an agreement on the desired model using a global unique identifier for the experiment run. So we use this unique identifier to promote the experiment by updating a production branch of the Git repo. And then upon doing this, the final model is pushed to a production endpoint and can be used for the downstream applications, right? So as I said, if you're familiar with AWS services, a lot of this may jump out at you, but this can get a bit complex as I talk through it. So I like to show a little bit of a visual after I've talked about it for a bit, and hopefully allows you to grasp the concepts a little better. Okay, so I wanted to go through a use case right now, just a customer success story. So it was a water utilities company. and obviously we worked on this, the customer had several machine learning models already designed and implemented in various environments, and they were seeking a consistent mechanism to quickly track the best experiment runs, as well as a managed hosting platform with automated deployment and promotion pipelines. So we proposed the Model Factory solution as a part of a phase one. We did a phased approach. And we tuned and integrated the models with ML Flow, right? So Model Factory supports ML Flow and Kubeflow. And ML Flow allowed us to track, package, and deploy models into the SageMaker platform. ML Flow is ML framework agnostic and provides support for TensorFlow, PyTorch, Keras, scikit-learn, Spark ML, etc. As part of the phase two of the engagement, we utilized AWS services such as Code Pipeline and Code Build to design and orchestrate the promotion pipeline for training and deploying inference endpoints and batch jobs. So essentially what we stood to achieve through this ML pipeline is that it facilitates and ensures a quick turnaround time for training and deploying models to production. So some of the AWS services we used were SageMaker, EMR, Code Pipeline, Code Build, which are part of the AWS Developer Tools suite. Athena, which is an ad hoc query service from within AWS. S3 for cloud storage, and ECR, which is that Elastic Container Registry I touched upon, is the Docker Hub in AWS. Some third-party applications that we use were Python, MLflow, TensorFlow, Horvath for distributed training, Petastorm for accelerated ingest into TensorFlow using Parquet. And some of the outcomes were, the customer was able to consistently package and deploy all of their models. They were able to track and compare their parameters and accuracy metrics across different experiments. They are able to uniquely identify each experiment run now, each model run, and any associated artifacts as well, using that unique ID I touched upon. And it doesn't matter, it's irrespective of the ML framework utilized as well. They were also able to get a quick turnaround time to pre-processing, training, and testing the models by simply checking in the model code changes into their source control. So that is it for my talk. I appreciate everyone taking the time. As I said, it can get a little complex. So please do contact me after the fact. Ask questions now. We do have a few minutes now for questions, but you can also reach out to me after the fact. My email is on the slide here. My LinkedIn is on there, so you can ask me any questions. You can reach me at any time. And I appreciate all your time today.